Welcome. Are you ready to take a look at one of the only math-intensive topics you're likely to see in the biochem section on test day? If so, you're in the right place, because in this short lesson, we'll be taking a look at Hardy-Weinberg equilibrium problems, both in theory and in practice. These problems have been a constant MCAT staple, so we're going to make sure you are ready to see them on test day. In this lesson, we're not only going to use the Hardy-Weinberg equations, we're going to learn what they actually mean and how the two equations are related to each other, and how that might help you on test day. Let's get started. Take a few moments to read over the scenario in your lesson book. In addition to just reading the prompt, try to really focus on remembering what's required for a Hardy-Weinberg equilibrium to exist. Okay. So we're in a population that has a really small but present group of giants. We're told that gigantism is recessive and the population is in equilibrium. In order to say that Hardy-Weinberg equilibrium conditions apply to a population, there must be no evolution within the population. That means no mutation, no drift, no natural or sexual selection, no population movement, nada. Essentially, there's absolutely no force changing the amount of each of these alleles in the population. That's what equilibrium means, no net changes over time. So we can expect both of these alleles to stick around for a while. The problem's also given us some numbers. It's prime material for a Hardy-Weinberg calculation. You probably already have the Hardy-Weinberg equations pretty much memorized, and we put them on the page for you as well, but that's not where we're going to focus on at first. After all, we're not going over this problem just to make sure you can solve this calculation. The goal for today is to make sure you understand how to deal with any version of a Hardy-Weinberg equilibrium problem. So instead of just diving in to plug and chug, let's actually just stop and think about our population. So we've got two groups of people. What are their genotypes and phenotypes? Well, for one, we definitely have giants. The prompt actually tells us exactly how many of those we have. We also know the genotype for all giants. It's a recessive trait, so their genotype must be all recessive. Because it's a height gene, we'll call it H, so our giants must be little h, little h. Our other group of people is our normal height portion of the population, but they get a little bit tricky because technically there are two genotypes for the phenotypes of normal. We know that some people have the little h gene but aren't actually expressing it. Those are heterozygotes. They look absolutely identical on the outside to anyone who's homozygous dominant, which is our third proportion of the population. Because these two groups are identical phenotypically, by just physically looking at a population, you can't actually guess how many people are carrying the recessive gene. The Hardy-Weinberg equilibrium is actually really useful for this, and as we'll see today, will help us figure out what the genotype ratios look like in this or any other Hardy-Weinberg applicable population. Now, let's put things in terms of that Hardy-Weinberg equilibrium equation. The variable p is defined as the frequency of the dominant allele. That means that in this system, p represents the frequency of big H. Note that it doesn't represent the frequency of any people. This is a measure specific to the gene itself. It tells us how much allele big H is out there in the population. Likewise, q, or frequency of the recessive allele, would relate to the frequency of little h in this population. Let's relate back to our population. How do the Hardy-Weinberg variables correspond to the population described in this problem? If someone is homozygous dominant, they would have not just one, but two big H alleles, which we can translate to P times P. A heterozygote would thus be P times Q, and a homozygous recessive person would thus be Q times Q. We're just subbing out one variable, H, for another variable, P or Q. By now, you should already be seeing some connections to the actual Hardy-Weinberg equations. Now we can start to really attack this math. If someone is homozygous recessive, we know their genotype is little h, or Q times Q. We also know that in this population, we had 9 giants out of a total of 10,000 people. Knowing that information, use your lesson book and solve for the value of Q. Let's run through the math together. Q times Q, or Q squared, was equal to 0.0009. To solve for Q itself, we would need a square root, which would give us 0.03. Now we have one of the major values needed for our Hardy-Weinberg equilibrium equation calculations, the value of Q. Now that we've got the value of Q, it is really easy to just plug in and solve for P. But how this equation works is pretty exciting. Let's think about our population again for a second. We already know that there are no other alleles for this gene locus, and the system is in equilibrium, which means big H and little h represent 100% of the population. There's no one who doesn't have these genes. That's part of why the no mutation condition of HardyWeinberg equilibrium is so important, because by definition, if there's no evolution, the frequency of big H plus the frequency of little h must represent the whole population. Which equation is this analogous to, and how could we use that to solve for P? As you probably saw as soon as you opened to this page, we were given the P plus Q equals 1 equation, which is just a restatement of the idea that these two alleles make up 100% of the population. So we can plug in our Q value from the previous prompt and solve for P to get a P value of 0.97. That means we now have all the base values we need to start considering any other genotype possible in the population. We are nearing the finish line. The final step for this problem will involve using another HardyWeinberg equation. So let's make sure we understand what that second equation actually is, what it means for us, and how you can remember to use it on testing. We'll start with the equation we were given. P plus Q equals 1. Let's test your memory of algebra for a second. What operation can I do to this whole equation in order to generate that second equation? I can square it. If I square the entire equation, it will stay equal to 1. But I now have a new equation to work with that will mean something unique in the given scenario. You might be wondering why you would want to square the equation in the first place. Well, each person in the population can carry more than one copy of an allele. They can carry 2. If I want an equation that allows me to calculate genotype frequency, it has to be one that allows for solving for the probability of each genotypic possibility. The variables P and Q alone don't tell me about real people because I need 2 alleles to have a whole person. Squaring will give me all possible 2 allele combinations. It's perfect for predicting what the actual people in the population will look like. Once I square the equation, I should get P plus Q times itself equals 1 before I finish multiplying through. I want you to stop right here for a second and think. If someone has P and Q, what does that remind you of? It's a heterozygote. So this is a heterozygote being multiplied by another heterozygote. In other words, this calculation is just doing a heterozygote cross. Go ahead and write in a heterozygote cross for this population using big and little h in the Punnett square on your page. Okay, now take a look at the square. We've got big H, of course, and then we have not 1, but 2 offspring heterozygotes. So if you ever find yourself forgetting where that 2 goes, or if there's a 2 in the second HardyWeinberg equation, remember how we were able to generate that equation mathematically, and also remember it's really just doing a heterozygote cross. If we do the pure math, this validates our conclusion. We wind up with P squared plus 2PQ plus Q squared equals 1. So we've got to use that 2 when calculating heterozygote frequency. It's key to the equation. Also, remember what the equation is telling us overall. It's just saying that if we counted up everyone of every genotype, we'd have 100% of the population. Now you've earned this final calculation, so see it through. Calculate out the number of heterozygotes in the population. If we solve for 2PQ, given our P and Q values from the previous prompts, you should get 2PQ equals about 0.06, or really 0.058. You'd want to round it on the MCAT though, unless the answers were really close together in the answer choices. At this point, all that's left, and don't forget to do this, is to actually calculate the real population value. So we just multiply by the number of people in the population overall, 10,000, and wind up with 580 heterozygotes. What does this tell you about the overall genotypic balance in this particular population? It must really favor homozygous dominant individuals because the vast majority of people weren't heterozygous or giants. This won't always be the case though, so be careful not to generalize from one HardyWeinberg problem to the next in that way. In this lesson, we took a look at how to solve problems using the HardyWeinberg equilibrium equations, including how to actually use those variables and what they stand for, which means you're going to be able to apply them on test day. Make sure to get some practice before then so that you're sure you can apply both of these equations if you see a situation that requires them on the real exam.